of all, how do we go from one dimension to three dimensions? If we're going to start off in one dimension, we ought to have counterparts for the concepts that we encountered in one dimension in three dimensions. In one dimension, we had a wave function, which was a function of position and time. In three dimensions, our wave function is going to be a function of position in three dimensions and time. Thankfully, it has not become a vector function. It is still only a scalar function, but it is now a function of 4 variables instead of only 1, or instead of only 2 here. We will see shortly that when we were talking about the time-independent Schrodinger equation, as derived from this full time-dependent wave function, we ended up with the solution to the time-independent Schrodinger equation were simply a function of position times e to the minus I energy time over h bar. We're going to find out something very similar happens in three-dimensional quantum mechanics. We'll get a function of position in 3 dimensions multiplied by the same exponential factor, e to the minus I energy time over h bar. The operators that will appear in the Schrodinger equation, for instance, in one dimension, we had, for instance, the position operator x hat and the momentum operator p hat. X hat and p hat in 3 dimensions are going to be vector operators. So instead of just having x hat, I'll have x hat, y hat, and z hat in a vector, or px hat, py hat, and pz hat in a vector. And the definitions here are more or less what you would expect. For instance, let's just say px hat is going to be minus I h bar derivative with respect to x. I have to start being more careful about the difference between total derivatives and partial derivatives now, since we're talking about functions of multiple variables. But hopefully the notation will become reasonably clear shortly. The full momentum vector operator here is going to be written then in terms of partial derivatives of x, y, and z, and we have some notation for that. Minus I h bar times this upside down triangle with a vector hat on top of it. This is the gradient operator from vector calculus, and this is going to be read as del or grad, or the gradient of, depending on whatever it's acting on. And this gradient operator here, as before, let me move this out of the way a little bit so my notation is less confusing. This full vector momentum operator is going to be minus I h bar and then partial derivative with respect to x, comma, partial derivative with respect to y, comma, partial derivative with respect to z. So that's my momentum operator. The position operator behaves similarly. X hat here is going to be x coordinate multiplied by whatever you're acting on, the wave function. Similarly for y hat being y coordinate multiplied by, and z hat being z coordinate multiplied by. We also have counterparts for the sorts of expressions we got working with something like the normalization of the wave function, the inner product of the wave function with itself in 1 dimension, or the inner product of the wave function with itself in 3 dimensions, still going to be equal to 0. Whereas in 1 dimension, we had an integral from minus infinity to infinity dx of psi star psi for our inner product. In 3 dimensions, we have to be a little more in depth. We have to integrate from minus infinity to infinity dx, and from minus infinity to infinity dy, and from minus infinity to infinity dz. But the same sort of expression is going to be the integrand. We're just going to be working with psi star times psi. Whereas this had to be, good grief, Brant. The wave function is normalized, not equal to 0. The inner product of the wave function with itself is equal to 1. Our normalization integrals are equal to 1. And that's going to be true whether we're talking about 1 dimension or 3 dimensions. So for every 1-dimensional structure, we end up with a 3-dimensional counterpart. Our wave function is going to be a function of multiple variables, and consequently we're going to have to keep track of multiple coordinates and derivatives with respect to multiple variables. And when we do things like normalize or calculate expectation values, we're going to have to be integrating over multiple dimensions. The Schrodinger equation also converts to 3D more or less how you would expect. This is the Schrodinger equation as we wrote it at the beginning of the course, in all its generality. We have I h bar times a partial derivative with respect to time being equal to a Hamiltonian operator acting on our wave function. If I write this I h bar partial derivative of psi with respect to time and expand out what the Hamiltonian actually is, in terms of general operators, p hat squared over 2m acting on the wave function, plus the potential energy, which is now going to be v as a function of 3 dimensions, v of x, y, and z, multiplied by the wave function. This p hat squared operator now is a little bit more subtle. We have to think about what it means to square a vector operator when it acts on the wave function. But we're going to have 1 over 2m times p hat. And since these are vectors, we can calculate the square by taking the dot product. These aren't vectors, of course, they're vector operators. They're still going to be acting on the wave function. V psi, we don't really have to worry about. That's relatively simple. Now, this vector dot product here, what is that actually going to look like? Well, we're going to have p hat, which I told you before was minus I h bar times the gradient. Well, if I take both the minus I h bars and pull them out front, I'm going to get minus h bar squared, which looks familiar from what we had before when we were talking about the kinetic energy operator. P hat then is going to be derivative with respect to x, derivative with respect to y, derivative with respect to z in a vector. I'm going to be taking the dot product of that vector with, well, itself more or less to find out what this p hat is. But this p hat is directly acting on psi itself. So I'll write this as derivative with respect of psi with respect to x, comma, derivative of psi with respect to y, and derivative of psi with respect to z, all together in a vector. And since I'm taking the dot product here, I know the x component of this vector and the x component of this vector are going to be multiplied together. So I'm going to be acting with the x derivative on the x derivative, the y derivative on the y derivative, and the z derivative on the z derivative. And I'm going to be adding up all of the results, since that's what you do when you're taking a dot product. The result then is going to be minus h bar squared over 2m times second derivative of psi with respect to x plus second derivative of psi with respect to y plus second derivative of psi with respect to z, plus v times psi as before. There's notation for this as well, since it appears over and over again. This guy we write as del squared. This is called the Laplacian, and it's either read as del squared, or you may hear this symbol called nabla. Nabla squared, the Laplacian, del squared, it all refers to the same sort of thing. And this is nice because this is a geometric operator, and it makes no reference in this notation to the specific structure of the partial derivatives that are necessary to compute it. So this is something that is a geometrical object, really. It doesn't have anything to do with the coordinate systems that you're working with, which simplifies the notation a great deal, and also allows us to go from one coordinate system to another with much more ease. So our final Schrodinger equation in 3 dimensions now, the way we're going to be working with it in this chapter is I h bar times the partial derivative of psi with respect to time is equal to minus h bar squared over 2m times the Laplacian of psi plus v times psi. So that's our Schrodinger equation in 3 dimensions. This is the full time-dependent Schrodinger equation. Notice we have these partial derivatives with respect to time. So when I'm writing psi in this equation, it's psi of x, y, z, and time. Or if I was writing this in spherical coordinates, I would have r, theta, and phi, and time all together. One of the first things we did with the Schrodinger equation when we were talking about one-dimensional physical systems was to do separation of variables to try and separate the time dependence from the position dependence. We can do that in 3 dimensions as well, and it works more or less how you would expect. We have our overall time-dependent Schrodinger equation, and we're going to be looking for solutions to this of the form psi of x, y, z, t, for instance, being equal to some function of x, y, and z multiplied by some function of time. I ran out of space here, but that's what this is going to look like. We're going to look for separation of variables type solutions to this formula, or to this equation. And you can see, remembering the definitions of the Laplacian here, it only had derivatives with respect to position in it. The potential operator here, v, is a function of x, y, and z. There's again no derivatives with respect to time, no time dependence in this part of the equation. So the left-hand side of this equation is where all the time-dependent parts of the Schrodinger equation are going to become significant. So when I substitute psi as a product of r, a function of position, and t, a function only of time, into this equation, I'm going to get something rather straightforward. When I substitute r times t into a partial derivative with respect to time, the partial derivative with respect to time will act on t, but not on r. So my r can be written out front. I'll have r times I h bar d capital T d time. The right-hand side, this has derivatives with respect to space. For instance, this del squared here has second derivative with respect to x, y, and z in it, if I'm writing things in Cartesian coordinates. It doesn't have any partial derivative with respect to time in it, so I can pull my time part out front. So I'll end up with minus t times h bar squared over 2m del squared r, when I substitute r times t in for psi here. Likewise, I'll end up with v times r times t here. This is just simple. So I can actually factor out the time from the right-hand side of this equation. And to fully separate the position and time dependence, I'll take this whole equation and divide it by RT. And when I do that, I'll get I h bar over t times partial derivative of time of the t part with respect to time being equal to 1 over r times minus h bar squared over 2m del squared r plus vr. Pardon me. This is the same sort of structure as we got when we were doing separation of variables in one dimension, except now instead of separating one spatial dimension from one temporal dimension, I've separated 3 spatial dimensions from one temporal dimension. The separation works the same way. We have here on the left a function only of time, and on the right a function only of space. And if this equation, the Schrodinger equation, is going to hold at all positions and all times, I have to be able to plug whatever value of t and whatever value of x, y, and z I want into this equation and have it still hold. The only way for this to work is if these functions are rather boring. These functions have to be constants. These are the constants that we got when we did separation of variables before, and last time we called it E. Since you know where this is going, E is going to be the energy. So these left-hand side and right-hand side are both going to be constants. And it turns out the left-hand side being equal to energy is going to give us the exact same solution we got before. This equation, if I multiply through by t, divide through by I h bar, gives me partial derivative of t with respect to time is equal to minus I e capital T over h bar, which has the same sort of solution. It tells us that capital T as a function of time is going to be equal to, or at least proportional to, e to the I energy time over h bar. I forgot a minus sign. E to the minus IET over h bar. This is exactly the same as the equation that we got when we were working in one dimension, which is good because we peeled off 3 spatial dimensions. The temporal dimension is relatively unchanged in this process. We haven't gone to multidimensional time after all, thank goodness. The spatial part being equal to time, if I'm going to say this is equal to energy, the right-hand side here being equal to energy, I can multiply through by r. And this r equation now takes the place of our psi of x, our position part of the Schrodinger equation. The contents of this parentheses here are is the Hamiltonian operator acting on the wave function. So what we end up with for our position part is, as before, h hat psi of x, y, and z, for instance. I'll just write it as psi of x since I don't want to commit to a coordinate system at this point. But psi of the spatial part of the wave function is the energy times the spatial part of the wave function. Note that the psi here is a function of x, y, and z only, whereas the psi here is a function of x, y, z, and t. I'm just going back to the notation we used when we were talking about one-dimensional functions, where psi could either represent the full time-dependent wave function or just the spatial part for the wave function. Griffiths uses lowercase psi for the spatial part and uppercase psi for the full time domain part, but I have a hard time distinguishing between lower and uppercase psi's in my handwriting. So, at any rate, you get the idea. We end up with the same sort of time-independent Schrodinger equation in 3 dimensions as we did in 1 dimension, except now we have to work with 3 dimensions, so instead of just having a derivative with respect to x here, we have derivatives with respect to x, y, and z. So this is really the same as we got before, only much more complicated. And the complications are going to make our life somewhat interesting over the next couple of days, which is really where a lot of the rich structure of quantum mechanics in the real world comes into play, because we'll start talking about things like angular momentum. And angular momentum turns out to be really crucial to the structure of atoms and molecules. That's about it for quantum mechanics in 3 dimensions as far as the overall structure of the Schrodinger equation goes. In order to check your understanding here, think about x hat and p hat and calculate the commutator. This, as before, is going to be x hat, py hat here, now minus py hat, x hat, where x hat is going to be the x coordinate operator, for instance, just x times whatever the operator is acting on, whereas py hat is going to be minus I h bar partial derivative with respect to y, having to do with the y component of the momentum. Work out the commutator of these, and then think about what this commutator implies in the context of the generalized uncertainty principle, which we studied in the last chapter. Can I measure both x position and y momentum as precisely as I want? Or what about x momentum and y momentum? You know from 1 dimensions that you can't measure x position and x momentum, but what about x position and y momentum?